So welcome to the afternoon session. And the first talk is by Ankur Moitra. Tell us about robust statistics revisited.
Great. Thanks. I changed the title, but same theme at least. So this is based on joint work with Elias Diakonikolas, Jerry Lee, Gautam Kamath, and Daniel Kane. So let me tell you at the outset what this talk is about. So this talk is about having your cake and eating it too. So getting estimators in high dimensions that are computationally efficient and are also provably robust. So before I get there, that's what I'm working up towards. Before I get to high dimensional robust estimation, let me start off with one-dimensional robust estimation. And before I do one-dimensional robust estimation, let me start off with one-dimensional statistics, just to make sure we're on the same page. So what you usually call classic parameter estimation is this broad class of questions. Imagine you're given samples from some unknown distribution, but it lives in some nice family. So this will be the example that we come back to many times, but in high dimensions. So for example, in one dimension, you could be given samples from a Gaussian, but you don't know its mean mu and its variance sigma squared. And the question is, first, can you accurately estimate its parameters? So, the answer to this is a resounding yes, obviously. In fact, you could use just the empirical mean, take the average of your points of their values. That converges very quickly to the mean mu. And you can take the empirical variance, and that converges very quickly to the true variance. So this is classic parameter estimation. And in fact, it's one example of a much broader paradigm, which is maximum likelihood estimation, which is something that was pioneered by Fisher, who developed a lot of the basic theory in the early 1900s. And the empirical mean and empirical variance are just two cases of this maximum likelihood estimator. So there are a lot of wonderful properties about the maximum likelihood estimator, things like, when you take enough samples, it really does converge to the true setting the parameters under tame conditions. In fact, it's even optimal in some sense because it actually has the smallest possible variance eventually as you take the number of samples to infinity. So a lot of times you hear this introduction about the maximum likelihood estimator in the theory talk. One of the starting points is, but how do you actually compute it? And then you ask, are there computationally efficient procedures instead? So today I'm going to take a different jumping off point, which is following the lines of Tukey, who asked questions like, all right, so the maximum likelihood estimator is great and works when you really are given samples from some true model. But what about errors in the model itself? What if you're given samples that aren't quite from a Gaussian? In fact, in Tukey's famous work that launched the field of robust statistics, he asked exactly this question about one-dimensional Gaussians. What he did was he took a one-dimensional Gaussian and he added noise to it. In his case, a Gaussian with larger variance, and studied empirically how many of the existing estimators performed. Now you can take this and it becomes an entire field, a family of questions, which robust statistics, there are tons of books and papers on it, which really ask questions of the flavor. Well, what estimators behave well in a neighborhood around the model, as opposed to working just when you're given one particular model? So this will be the setting that we talk about. And let's actually build up the notions from robust statistics in the one-dimensional case before we move on to high dimensions. So let's revisit this one-dimensional Gaussian learning problem from the perspective of robust statistics and talk about what happens when there are errors in the model itself. So this will be the question, but it'll take me a couple slides to actually formalize what I mean by the noise and what I mean by learn the parameters in the presence of noise. But roughly the goal is the obvious one is, instead of actually getting samples from this idealized model, we're getting samples from this actual model, which isn't quite Gaussian, but it's close. And we can think of the noise as being the difference in their PDFs, and we want to be able to recover the parameters in spite of the fact that the samples aren't really from a Gaussian.
So this is PDF, you're not convolving the Gaussian with that noise there.
Yes, so I'm not convolving it. Let me describe what I mean by the noise for simplicity. So how are we actually going to constrain this noise? There are a lot of ways that make sense. Let me tell you a very natural way. So one way, and there are actually two equivalent ways of thinking about this, is if you take the difference of the two PDFs, one way you could constrain the noise is just by constraining the L1 norm of that difference. So ensuring that whatever that difference is between the idealized model and the true one, isn't too large an L1 mass. Now there's another equivalent way to think about this. We think about the L1 norm being at most O of epsilon. You could instead think about this as, imagine that someone takes a bunch of samples from a Gaussian, but then the difference between these two PDFs is where you're actually changing the samples in your set. So another way to think about this is it's like the adversary is corrupting about an epsilon fraction of your points. In fact, all of the results in this talk are going to work with the even stronger model, where you imagine an adversary takes a bunch of samples, can look at them, and then decide which epsilon fraction of them to corrupt completely arbitrarily. So this is our model for noise, is that our adversary has absolute control over about an epsilon fraction of the points. This actually generalizes many of the standard models in robust statistics. One of the most famous examples is Huber's contamination model, which corresponds to the constraint that an adversary is only allowed to add samples to your set instead of actually subtracting them in some places. So in any case, this will be how we constrain the noise, and just introduce a little bit of nomenclature. I'm going to call the outliers the points that the adversary has touched and has moved in arbitrary ways. And the things that actually the adversary didn't touch, I'm going to refer to as inliers. So this is how we constrain the noise, and the only other thing left for me to formalize this question is to try and set the goal. So if this is our model for noise, well, how do we want to measure the closeness of the parameters that we're striving to learn? So in what norm do we want to make sure that the parameters are close to the true parameters that we're given noisy access to? In this case, there's a very natural norm to do it, is the total variation distance, which is just half of the L1 distance between the two PDFs. Why is this the natural thing? Is because the way that we've set up the adversary, he's arbitrarily corrupting an epsilon fraction of the samples. Well, that guarantees that whatever our observed distribution is, the total variation distance to the idealized distribution is bounded by epsilon. The difference between these two is exactly the thing that we constrain the L1 norm of. So in this problem, we're given samples that come from a distribution that's epsilon close in total variation distance to a Gaussian. So the natural goal then is to find another Gaussian that's close in total variation. So if you're given samples from something that's close in TV, find something else that's also close in TV. So you can state this goal two different ways. You could be looking for an estimate, which is a Gaussian, whose total variation to the ideal one is O of epsilon, or you can think about it as actually finding the best approximation among your family of hypotheses to whatever you're given samples from. So this is the type of question you'll be interested in. Given samples that are epsilon close in TV, find something else that's about epsilon close in TV. It's a very natural question, and first I should tell you a little bit about what's known in robust statistics. So first, when I asked the question non-robustly, there was an obvious choice for how to do it, was the empirical mean and the empirical variance. And the first question we should ask is, in this type of model where an adversary is allowed control, do the empirical mean and empirical variance still work? And in this case, the answer is a resounding no. In fact, many of you probably know the reason for this is because if the adversary has control over some small fraction of samples, what he can do is he can put a tiny little bump in the distribution. Now that bump he can push arbitrarily far out, and the result is that the mean of this distribution is diverging to infinity as he pushes that bump further and further out. In fact, the variance is diverging to infinity too. So what this means is the statement that a single corrupted sample can arbitrarily corrupt the estimates of the empirical mean and empirical covariance. So what should you actually do to estimate the mean and variance in these types of robust statistics models? Well, I think many of you might be able to guess what you can do with the mean. So does anyone have a guess what you should do?
Median.
The median, right? Now what about the variance? Any guesses? Well, if the median works, how about doing a median of medians? That's called the median absolute deviation. And this pair actually does work. So let me tell you a folklore fact about this pair of estimates, that if you use the right scaling constant for this median absolute deviation, you take the median, then this has about as good a statistical guarantee as you can hope for. You're given samples that are epsilon close in total variation to a Gaussian, and what it learns with the median and the median absolute deviation is something that's epsilon close in TV. That's great. So it completely solves this one-dimensional statistical problem. And you could also call this properly agnostically learning a 1D Gaussian. That's another way. But now I can get to what's the main point of this talk with this. Yep.
Quick question. So the hats are random variables. So is this an expectation or what type?
Yeah, these are with, the way I stated it here, it's with constant probability, but there's some log 1 over delta dependence on these things. But I'm going to suppress all of the with high probability types of statements, but good question. Now I can get to what's the main question that I'm going to be interested in. With this as the backstory about robust statistics and what's true in one dimension, the natural question is, what can you do in high dimensions? And in fact, we have all sorts of high dimensional data that are not just not living in one dimension, but are truly high dimensional. So one of the examples to keep in the back of your mind are things like microarrays, which really you're working with about 10,000 different genes. So your data points might actually live in some huge dimensional space. So what's actually known about high dimensional robust estimation, even for this problem? So the question I'll be interested in, this will be the main problem for this talk, is the natural generalization to high dimensions. Given it's such a basic question, it's surprising that the bounds were so wide open, what was true here. But here's the question. Given samples from a high dimensional Gaussian, with something close to a high dimensional Gaussian, can you learn anything else that's close in TV? So something that's roughly epsilon in TV. And there are going to be two special cases that I'm going to pay special attention to. Once we solve these two special cases, we'll actually be able to solve the entire thing. So one special case is when I promise you the covariance is the identity. In that case, all you're trying to do is find this high dimensional mean that I'll call the unknown mean case. And another case, which I'll promise you that the mean is 0, and all I want to do is find this high dimensional covariance. These subproblems are like trying to figure out what is the high dimensional analog of the median and the high dimensional analog of the median absolute deviation. That's what we'll need to do to solve these two problems. So let me tell you what's known. In fact, even in just the special case of the unknown mean, it's kind of interesting if you go through all of the existing approaches. So one of the standard approaches within robust statistics is what's called the Tukey median. So it's not so important what this is for this talk. It's some notion of the deepest point among a cloud of points in high dimensions, but it's a difficult thing to search for. Now, it has a fantastic error guarantee. So if you could compute the Tukey median, if you were given samples that were epsilon close to a Gaussian, you would learn the mean within distance epsilon. That's terrific. But the problem is that it's well known to be NP hard to compute it. So you're stuck with estimators that really only make sense in very low dimensional problems for this type of approach. Now maybe that's just the wrong way to generalize the median to high dimensions. Another way that you can try generalizing the median to high dimensions is the geometric median. That looks for the point that minimizes the sum of the Euclidean distances instead of the sum of squares of the Euclidean distances. That's not only polytime computable, you can even compute it and approximate it in nearly linear time. But the trouble is that it achieves a really awful error guarantee. So how close is it as a function of the dimension? Well, you've got the epsilon, but you also have a root d sitting here. So it loses a polynomial factor in the error guarantee that depends on the dimension. And I'll go into more details about why this is really, really bad in the next slide. But first, let me finish my discussion of this previous literature. There are other things you can do, like tournament estimators, where what you do is you look over large subsamples of the data set. Each one of them gives you an estimate for the mean, and you would run some sort of tournament between these hypotheses. That gets error O of epsilon, but it runs in time n to the O of d, so again, infeasible in high dimensions. You can do something else that's called pruning, which is just when you're given points in high dimensions, maybe you throw away all the points that are just stupidly far away from the other ones. That actually you can do really quickly, but again falls into this trap of having error O of epsilon times root d. So there are tons more, but I'm running out of space on this slide. Yep?
So these bounds, even poly d and n, make sense to me only if n is polynomial in d, in terms of, because you've not talked about how many samples you actually
That's
have.
right. So for all of this, I'm going to be talking about n being polynomial in d.
And that's sufficient, because you didn't state a theorem of that kind, whether it was sufficient to get O.
Yeah, so I will when I get to the main theorem results, but I should warn you as a caveat that my goal here is just to see what's true in high dimensions with polynomial sample complexity, and trying to understand whether you can do this with nearly optimal sample complexity. I have no idea, and that's a great open question. Yep?
And the error is like you have the actual median, and then you look at it's a multiplicative error?
So this isn't TV, because total variation is a great way to measure it, because you're given samples that are close in TV. So you want to find something else that's close in TV. The other way to think about it is if you choose the wrong norm to measure your parameter distance, it's very easy to hide polynomial and the dimension factors. And this way you have to be honest about whether or not there are such factors. In any case, we could call this, because we're theorists, some type of price problem, right? Maybe this is just the price of robustness, that all of these known estimators are either hard to compute or they lose polynomial factors in their dimension. And what I want to do first is I want to emphasize why this is really awful, that they lose these factors. One way to think about it is that, total variation distance is always at most 1. So in fact, how small does the error need to be to have any non-trivial error guarantee? You need the fraction of errors to be at most 1 over root d. That's what's so bad about it. Or to put it concretely, for these microarrays, you're talking about, even without worrying about what the hidden constants are, you can only tolerate 1% of errors at most, even though in principle, robust statistics tells you can tolerate much higher fractions. We just don't know how to compute those estimators. So this is my goal, is to understand what should be true for high-dimensional robust statistics. Can you have your cake and eat it too? All right, so is robust estimation algorithmically even possible in high dimensions? It's not so clear from this discussion. Yep?
Does this have to be all of epsilon, or can you get epsilon plus something which depends on the number of samples that you have?
For those estimators?
Yeah.
It's always, you mean what do those?
Well, let's say, disregarding the computational concentration, can you get epsilon plus whatever, 1
This is actually not a sample complexity issue, that those estimators, when they get epsilon times root d, they would still get that even if you took a much larger polynomial number of samples, because your adversary just has control over the same fraction of samples it did, and it doesn't actually help. It's still,
No,
non-computationally.
not computationally. Can you get like epsilon plus something?
Can you make the big O in the first row? Can you make the big O like 1?
Sorry, so the question is, what are the information theoretic limits if you throw away?
Information theoretic, can you get instead of like twice or 3 times?
Let's table that question, because see, the point is that, so when Huber studied this, he studied it in a minimax setting, but in fact, every time you change the model and you make it stronger, the adversary can see the samples and then change them, then that actually strictly changes the constant. So a bunch of these things, it's not so clear what the optimal constants would be. And there are cases where I can say more later, but, right now we only have epsilon times root d. I haven't asserted anything yet, so let me assert something stronger. So here's our main result, is that actually you can do robust estimation in high dimensions without losing dimension-dependent factors. So in fact, so the sample complexity here is polynomial, but it's suboptimal in that way. It's a very interesting question to try and get something with d over epsilon squared, but let's table that issue. Given samples that are epsilon close in total variation distance to a high dimensional Gaussian, you don't know either the mean or the covariance, so the full problem, then you can actually in poly time compute estimates mu hat and sigma hat, which how close are they? There's no d's in that. It's epsilon times poly log 1 over epsilon. So in fact, you get non-trivial guarantees even for epsilons which are constants independent of the dimension. And that's the main result. In fact, there's another way to think about this, which I like and fits into the theme of this workshop, is actually not only do things like the Tukey median work for robust statistics if you could compute them, but they're basically the only things that work. So when you actually learn some mu hat and some sigma hat that really is close, what you're really doing is you're approximating the Tukey median and some of the high dimensional robust variances in an interesting semi-random model where many of the samples did come from a Gaussian. So a lot of these worst case hardness guarantees actually do go out the window when you have the right model, things like Huber's contamination model. So that's, I think, one of the other cool punchlines. Now, actually, our paper had so many authors because it was the merge of 2 different papers. Around the same time, there was yet another paper. So there were some results of Lai, Rao, and Vempala, which study the same problem. Now, comparing parameter distance to total variation is a little tricky. But the way to parse this is that roughly what this translates to is that you learn the Gaussian within epsilon to the 1/2 times log to the 1/2 d in total variation. And the nice thing about their result and our result and many of the other things is that they do work for non-Gaussian distributions too. And once you know how to do these types of things, how to get high dimensional robust estimation, there's a lot of problems that suddenly become within reach. So in fact, there's a general recipe that I'm going to give you for how to do robust high-dimensional estimation. And across both papers, they get applications to different things. So we got some applications to product distributions, mixtures of spherical Gaussians. They got applications to singular value decomposition in the presence of noise and independent component analysis. But I won't really have time to touch on those more. Yep?
The previous slide,
Yep.
what was the model, the one where epsilon fraction are contaminated, or
Yeah.
where the adversary can see the samples and then
Adversary can see the samples and then decide which fraction to arbitrarily. Yep.
It's not the way you roll it. You roll epsilon closing total variation.
Yeah, that's right, because I'm going to focus on the simpler model, but it does work for that model. But this seems like a more compact way to state
The
it.
semi-random at the bottom.
Yeah, that's right. That's right. All right, so let me at least, yep.
Does this non-Gaussian distribution include non-symmetric distribution? Because then,
Non-spherically symmetric?
yeah.
No, no. The mixtures of the product distributions are non-Gaussian and are non-spherically symmetric, but those results actually do rely on being somewhat close to spherical. That's a good question. All right, so now that I told you at least the background of robust statistics, what was known before and what's known now, what I want to do in the remainder of the talk is I want to tell you that there's actually this general recipe for how to design robust estimators in high dimensions. So all I'm going to do in the rest of the talk is I'm going to explain what the different steps in this recipe look like. In fact, step 2 will be the key one, but let me start from the beginning. So let's focus on just the unknown mean case, where I'm trying to learn this mean mu, and I'm promised the covariance is the identity. And let's try and understand what this recipe looks like, and I'll go through it slowly. So the first step in this recipe is, total variation distance is a bit tricky to work with. It's a very natural notion of, the norm because of the model we're working in. But the first goal is to find a good parameter distance that works roughly as good for controlling the total variation. So what distance on our parameters will be good enough to guarantee that we actually are close in total variation distance? Here's the basic fact I'm going to use, is that if you take two Gaussians where the mean where the covariance is the identity, and they have different means, their total variation distance is bounded by the Euclidean distance between them. In fact, that's roughly tight, that if the Euclidean distance is epsilon, then their total variation distance really will be about epsilon in this case. This is really simple to prove, but I'm not going to prove it. The way that you prove these things is you use Pinsker's inequality, which relates the square of the total variation to the KL divergence. And the point is that there are well-known formulas for the KL divergence between two Gaussians. So when you plug in that formula and use it using Pinsker to bound the total variation, this is what you get out in the special case of the unknown mean. So this is the right metric to control total variation distance in this first case. And it tells us that our goal is to be close in Euclidean distance in high dimensions to the unknown mean. We want to get O tilde of epsilon close. That's our new goal. So this is step 1. All right, so now let me tell you what's the key step in this. For the unknown mean case, it's pretty simple. Is really step 2, which is let's try and use the naive estimators, the empirical mean to begin with. Now, many works that study robustness in high dimensions, what they do is they try and find all outliers. That's not what we're going to do. Instead, what we want to do is we just want to detect when our naive estimator has been compromised. When the adversary, in the points they've gotten the ability to control, has really moved the estimate away from the truth. So what would this look like? Imagine I give you a sample of points, which in high dimensions, they're roughly at the same distance away. Now, if the adversary has moved the empirical mean far away from the true mean, he could have done that by collecting a bunch of points in some low dimensional space. And how far would they be out? They'd be root d out, and they're epsilon fraction of them. So that's exactly where this epsilon times root d comes from, is that's how he would move the mean very far away.
Why do they have to be in this low-dimensional space? You can
So-
just take a subset and move them together.
This would be one way that the adversary could actually really badly corrupt you, is he could hide in some direction in high dimensional space and put a bunch of points that are root d away from the true mean, but then he actually moves your empirical mean along that direction by epsilon times root d. So this would be like one of the canonical ways that he would try and corrupt your estimates. Of course, he could do it not just in a line, but in a subspace and so on. Did you have a question?
If you move them too much farther, you could detect that just by
That's
moving
right.
farther. So it's
Exactly.
Like how far you can do it without.
Exactly. Because that's exactly the point, is that if I didn't show you what the colors were here, then you wouldn't be able to detect which ones were outliers or not. but you would know that there are many of them in some direction, so a lot of them are outliers. And if they were further away from that ball, then you really would know that they're outliers. So this is the most interesting case to try and figure out how the adversary can go about compromising the naive estimator. But now the intuition is very simple, is that when the adversary has done this, the point is that there is a direction in which the variance is too large. The variance should have been 1 in that direction if he hadn't corrupted any of the points, but when he really has moved our estimate very far away from the truth, he's created a direction which the variance is large. That tells us where many of the outliers live, and it tells us how to purify our sample. So you can make that precise. This is the key lemma. I'm not going to prove it. But this is the lemma that underlies the unknown mean case, is that it turns out that if you take enough samples and you compute the empirical mean and empirical covariance, then if the empirical mean is far away from the true mean, how far? At least epsilon times root log 1 over epsilon, then that means that there actually has to be a direction where the variance is noticeably off from 1. It needs to be 1 plus this quantity. So this is actually a meta statement. The important takeaway is that in order for an adversary to mess up the first moment, the mean, the empirical mean, there has to be an echo of what he's done in the higher order moments in the second moment. And you can detect that in that way. So if we had this key lemma, how would we go about designing an algorithm? So in our paper, we give 2 different algorithms for doing this. The convex programming is polynomial, but has better sample complexity. Filtering is faster and slightly worse sample complexity. But let me tell you the filtering approach. So how could we use this key lemma to actually design an estimator in high dimensions? The idea is to do a win-win analysis. Either you're going to find good parameters already, or you're going to remove many outliers. So if you, for example, detect that your empirical covariance is very far off from the identity, that the spectral norm is at least this C prime times epsilon log 1 over epsilon, which is the consequence of this key lemma, if the mean were far away, then what that means is that when you look at the direction of large variance, let's call that V, and you project on this direction, the variance is larger than 1. It's 1 plus epsilon. And in that direction, the only reason that there could be such a large variance is if the outliers disproportionately contribute to it. So it turns out that what you can do is you can find a threshold T so that when you just throw out all the points above that threshold, you're guaranteed that you throw out more of the outliers than the inliers. There are some inliers above it, but you're making progress towards purifying the sample. So what this means is that this immediately gives us the algorithm, is that what we do is we just hope the empirical mean works. We try out the empirical mean, but then we use the spectral test to see if it's a certifiably good estimate or not. If this empirical covariance has too large a top eigenvector, then what that means is we can use it as a direction to prune out many of the outliers. And eventually, if we continue in this way, we'd eventually run out of outliers, and we'd be left with an arbitrary subset of the inliers. And what we show is through concentration bounds, we show that actually any such set you're left over with would be a good estimate for the true parameters. Yep.
So don't you have the problem of dependence in the iteration number 2 and onwards?
That's right. So what you actually need to show is that for every 1 minus epsilon fraction of the subset of inliers, that actually would be a good estimate for the mean. That's what makes some of the concentration bounds so painful, is that you don't actually have control over which subset of the inliers you're left with. All you're guaranteed is that, at the end, you have whatever you have. Either you found certifiably good parameters that work via the key lemma, or at the end, what you have is an arbitrary subset, and that empirical mean will be good enough.
So this obstacle is what causes you to get like this log 1 over epsilon? Or is
That's right. That's exactly what causes the root log 1 over epsilon, but it also makes some of the concentration bounds more painful, because these are statistics that don't concentrate arbitrarily well as you take more and more samples, because you're quantifying over all 1 minus epsilon size subsets.
You could get over this issue, that maybe you could get rid of the log 1 over epsilon.
That's right. I'll talk about that more later. All right, so eventually find certifiably good parameters, and it's a kind of long paper, but let me just summarize the main result. So the running time we get is polynomial. So if n is the sample complexity, then we get n times d squared running time, and the sample complexity is d squared over epsilon squared. It involves some interesting tricks to actually prove that this works because of the dependencies between the iterations. And I'm not going to talk about the filtering approach, but instead let me...
What's the sample complexity for the one-dimensional case?
The sample complexity is 1 over epsilon squared for it, which is optimal. All right, so let me give you a brief glimpse of what the unknown covariance looks like. That's the more technically involved one. But the key point is that it actually follows the same basic recipe. So if you remember, all you have are these steps. First, you find a parameter distance. Then you figure out when the empirical estimate has been compromised. And then you build it into an algorithm. So how do we do this in the unknown covariance case, where the mean is 0 and the covariance is unknown? Once again, what you do is you find some distance between the covariances that's good enough to bound the total variation. This, once again, you use Pinsker's inequality, and this is roughly tight, that when this norm is large, you really do have large total variation distance. And it changes what our goal is. Our goal is to find an estimate that's close according to this metric. So we want to be O tilde of epsilon close. Distance seems a bit strange, but trust me, it is the right one. And let me get to the key point, so which is, step 2 is always where the action is happening, is how do we actually detect when the empirical covariance has been badly compromised? So in the case of the empirical mean, we saw this echo in the second moment. The same way when the empirical covariance has been compromised, there's an echo in the fourth moment. But things get a bit more interesting here. So imagine you get samples from n of 0 sigma without corruptions. What can we say about this empirical estimate sigma hat? Well, one of the key facts, it turns out, is that if you take samples from this Gaussian, 0 and sigma for the covariance, and you create this d squared by d squared matrix, what it really is the flattening of a fourth order tensor. So this is a length d squared vector because you're tensoring x with itself. You take its times its own transpose. Well, that actually has a very nice form, where it looks like 2 times sigma tensor with itself, plus something else, which is really you take the d by d matrix sigma, and you flatten it. That's why I use this flat notation, into a length d squared vector and take its transpose with itself. Now this might not look so intuitive, but let me tell you a little something about where this comes up, is that everyone knows that, for example, the fourth moment of a one-dimensional Gaussian is 3. There's a really pedantic way to say that, which is it turns out it's 3 because the number of perfect matchings in a size 4 graph is 3. Now there's a generalization of that fact, which is called Isserlis's theorem, sometimes also called Wick's formula, that allows you to compute moments of Gaussians based on sums over perfect matchings. And this is what allows you to get a nice form for what this flattening of the fourth order tensor looks like. But the important thing is you really have 3 terms here. You have 2 which correspond to the matchings that respect the way you flattened it, and one of the ones that doesn't. And that's the sort of tricky beast, because this spectrally is much larger than the other term. So this makes things very complicated, because if you hope that by corrupting your estimates, your adversary really changes the spectral properties of M, the problem is you have this other huge thing sitting in there that actually dwarfs whatever else is going on. So it turns out that there's a way to project this out, and essentially, instead of taking top eigenvectors, to look at restricted eigenvalue computations on M, which what it does is, what the overall algorithm looks like is you take a guess sigma hat, you transform it by sigma hat to the -1/2, and now if these y sub i's really were coming without noise, they would be from n of 0i, and we know exactly what their flattened tensor would look like, and we would know that this corresponding thing would have small restricted eigenvalues and remove that flattening piece. And this gives us a spectral test on this d squared by d squared matrix, which is really a way of doing the same thing, saying that if the second moments were messed up, there would be an echo in the fourth moments that allow us to actually detect many outliers the adversary has added. So I'll very quickly say that it turns out these 2 cases give you the overall algorithm. So what you do is when you're given samples from epsilon close to a Gaussian with unknown mean and unknown covariance, well, what do? You use the standard doubling trick. So you just take 2 independent samples from it. And that is close in total variation distance to being from a Gaussian of 0 and 2 sigma covariance. And now what you can do is you can use the algorithm for the unknown covariance case to learn sigma. And now when you actually take whatever your estimate is and transform the data, you're now back in the unknown mean case where you're trying to learn the mean, knowing that the covariance is the identity and that you're getting samples close to that. This turns out to be the right distance. You really want to look at Euclidean distance after applying sigma hat to the -1/2. In any case, this gives the overall algorithm just by combining these two special cases. So what I want to do just in the last 2-3 minutes is mention something that I'm excited about. First, once you have this general recipe, you can push it to lots of other things. So there are lots of other problems that you can give provably robust estimators in high dimensions that avoid polynomial and D dependence. For their error guarantees, you can do things like binary product distributions. You're getting worse dependence on epsilon, but there is no D here. You get things for mixtures of balanced product distributions. That 1/6 is definitely not optimal, but it's independent of D. And you also get things for mixtures of K-spherical Gaussians that don't have any Ds but do have Ks. Now the thing I'm really excited about is actually trying these things out. So the funny thing is, once you go back to robust statistics literature and you look at what's empirically known, actually not much is known in even anything moderate dimension. So I couldn't find anything that studied robust statistics in dimension larger than 6. So a lot of these estimators that they're proposing, they work very well in low dimensions, but as soon as you go to high dimensions, then all of a sudden they get really bad error dependence. So we tried out some synthetic experiments from noisy samples from a Gaussian, comparing it to at least 2 estimators that we can implement and don't run in exponential time, RANSAC and the geometric median. You can see here that as we vary the dimension, they really do behave very badly as a function of the dimension and the error guarantees they get. In fact, what's even worse is that even for dimension 50, they're giving almost vacuous error guarantees and how close they actually get. And this little line down here is our algorithm in terms of its error guarantee. So all of a sudden, you can actually do these types of things in high dimensions without paying this huge price of dimensionality. And I wonder what else you can do. So the thing I'm really excited about is to try and understand where else you can apply this now that at least some part of robust statistics is practically within reach. All right, so what I hope you got out of the talk was what I gave you was an algorithm for agnostically learning a high-dimensional Gaussian. So instead of error guarantees of epsilon times root D, what I got was epsilon times polylog 1 over epsilon for learning the mean and covariance. In fact, I gave you a general recipe for how to go about constructing robust estimators based on finding the right parameter distance and then turning it into a restricted eigenvalue problem which detects whether or not your empirical estimator has been compromised. And I gave you some other applications, other mixture models, and maybe I'll close with this question: is practical robust statistics within reach? All right, thank you.
When you said your algorithm in that graph, was it the convex programming based algorithm?
It was the filtering.
Okay.
It was the filtering. So the convex programming uses ellipsoid. So it's definitely not going to be runnable on these things. It has the advantage that theoretically we can prove much better things in terms of its sample complexity because we don't have to deal with this issue about the dependence between the different iterations like we do in the filtering. It's more of like a soft outlier removal. But what you can do here is you can just kind of hope it works and run it with lower sample complexity. It still does seem to work. So we can punt on this issue about whether we can actually handle the dependency between the iterations in a clever way and just try it out.
Did you tell me just 2 months ago that there's actually better implementations of ellipsoid than you might have expected?
That's right. It's still not good enough for this. Yeah.
How do these kinds of estimators relate to the unbiased estimators, like the James-Stein estimator or something like that, when it comes to robust statistics?
So you're talking about like the James-Stein shrinkage style estimators? Yeah, that's actually kind of a different beast because that's something that's not a maximum likelihood estimator and yet outperforms for small samples maximum likelihood. But I actually deliberately punted on that issue because maximum likelihood, I anyway said, is asymptotically optimal, which then the advantages of James-Stein actually go away in terms of the correction. I have no idea if there could be similar corrections that one could do to these types of estimators, but right now, the question is even what's the right practical version of this?
Okay, so I think maybe if you want to ask more questions, I can do it later and invite